Welcome to this section on training and optimization. In this section, we shall make use of the binary cross entropy loss in training our model. The optimizer we'll use is the Adams optimizer with a learning rate of 0.001. Now we define the accuracy, that's our train accuracy, which is a binary accuracy. We define the validation accuracy, the binary accuracy, the train true positives, which is a true positives. That's actually a metric which we've already called right here. So all these metrics we've gotten from TensorFlow's keras or TensorFlow.keras.metrics. We've imported all this. Then for the losses, we've imported the binary cross entropy. So we could take this off. That's fine. Now we have that. Go run this again and then get back to this. We have the true negative, the false positives, the false negatives, the false negatives. This comes twice, so let's take this off. The precision and then the recall. Now other metrics like the F1 score are also, and the AUC, that's the area under the curve, are also included in TensorFlow's keras.metrics package. Let's get back to our training. We can now define the training step. So right here we define the training step. We're working in graph mode, so that's why we have this TF, the function decorator. In the training step, what we do is we take in X and then Y. Obviously there's the inputs and then the labels. From the model, we take in X and then we predict Y. So here we have Y pred and then we have the true Y. Then the loss function, which has been defined already, that's the binary cross entropy loss, has been defined. Now computes the loss based on the actual levels and the predicted levels by the model, which is now put in this loss value variable, and that we shall return in our train step function. Now once this is done, we compute the gradients using the loss value and the model weights. Then once we compute these gradients, we can now optimize our model by taking in the gradients and the model weights. Then once this is okay, we could now update the different metrics, that's accuracy, the true positives, true negatives, false positive, false negatives. Let's take the AUC off, we're not going to work with that. The precision and the recall. Once all these are updated, we return the loss value, and that's fine. The next step is now the validation step. But there's a difference that we are not doing any training, so we don't have to get into the gradient tape, and we don't also have to optimize our model. So basically what we're doing here is we're getting Y pred based on this X, and then we're computing the loss value, and then we're updating the validation accuracy, true positives, true negatives, up to the validation recall, and then we output a loss value for the validation step. So that's fine. We've run this already, run that. Then finally we get to the training. For the training, we go for each and every epoch. We obtain for the training data set X and Y. We get into the training step, which we've defined already. We obtain the loss. Obviously the loss is from this, it's returned, and then we get this train loss. Again, for the validation, we take X and Y from the validation data set. We get the validation loss. And then since we've been updating this metrics, what we'll do now is, after obtaining this train loss and validation loss, we now print them out. That's we print out the train loss, print out the train accuracy by calling the train accuracy the result, multiplying by 100, the train precision by result, multiplying by 100, recall, multiplying by 100. Now the next is the confusion matrix, which we shall plot out. Now the way we do this is simple. We just have, because the confusion matrix is made of the true positives, the number of true positives, number of false positives, number of false negatives, number of true negatives. Recall that our aim is to ensure that the number of true positives are as high as possible, while the number of false negatives to be as small as possible, and in an ideal case, if possible, 0. So ideally we want this to be 0, we want this to be 0, we want this to be all the positives which actually exist in the data set, and this should be all the negatives which exist in the data set. In our case, the benign cells are considered to be negatives. So benign cells are negatives, while the malignant cells are positives. Now, it's also true that we had done this automatically from the TensorFlow's preprocessing.image dataset from directory package, but it's important to note that if you look at the ordering of the classes in the folders, the benign class comes before the malignant, and so automatically all the benign cells are considered to be of class 0 and then the malignant of class 1. So that said, let's continue with the printing out of this confusion matrix. Now, once we get to this, we simply have the train true positive the result, train false positive the result, false negative the result, and true negative the result. So we just printed out this values or this metric values based on what has been calculated previously. So let's take this off, run that, and now after getting to this, we now reset the states of all our metrics. So go from accuracy to true positive right up to the recall. We reset all their states, and so this is our last and final training step, which we now run. After training for several epochs, here are the results we obtain. We have the training set loss, accuracy, precision, recall, the confusion matrix, and the validation loss, accuracy, precision, recall, and the validation confusion matrix. We see how the accuracy keeps increasing for both the training and the validation set, and then it plateaus after a certain number of epochs. See here we have 90.64, 90.76 for the validation, 90.83. Yeah, we are 91. Let's continue. We come now to see the highest accuracy we obtain should be at 91, and here is it. It's obtained at the 33rd epoch. So here we have the accuracy 91, loss, and then the training accuracy 96, the loss 0.18. But from here the validation accuracy starts dropping. So we should normally stop training at that point, since after that it starts to overfit on the training data set. That's why you see the training accuracy keeps increasing while the validation accuracy starts dropping. So that's it. After 100 epochs, here we are, the validation accuracy 91. The loss has increased from 0.4 to 0.7, while the accuracy of the training set has increased up to 98%, and this loss has dropped to 0.07. So this means that at the 33rd epoch or around the 34th epoch, we were supposed to stop training. Now, although the accuracy starts to drop around the 32nd, 33rd, 34th epoch, note that the validation loss had already started increasing from the lowest loss it had achieved. That was around this year, the 18th epoch, where we had this lowest validation loss of 0.35, and then the validation loss started increasing. So you could also decide to stop the training once you get to this lowest validation loss. Now, there's also this precision and recall values, which have a difference of about 5%, as you could see here, 91, 95, 90, 95, which shows that overall we have a better recall as compared to the precision. Now, and from the formulas, where we have the precision, which is the true positive, or number of true positives divided by number of true positives plus false positives, this plus, and then the recall is number of true positives divided by number of true positives plus false negatives. It's clear that this higher recall value comes because the model does better at correctly classifying the positives. Hence, we have fewer false negatives as compared to the false positives. Since the model doesn't do as well in classifying the negative samples. Hence the reason why we have more false positives as compared to the false negatives. Also note that the benign samples that's of class 0 are considered to be the negative samples, and the malignant samples of class 1 are considered to be the positive samples. And so from our confusion matrix, we can come to a conclusion that the model does better at classifying the malignant samples, which are the positive samples, as compared to the benign samples, which are the negative samples. And this will also come from the fact that the number of malignant samples are around twice the number of benign samples we have in our data set. Since our data set is imbalanced, the model tends to better classify the malignant samples as compared to the benign samples. And so since the model is used to seeing mostly the malignant samples, it tends to make more errors when classifying a benign input. Hence we have many more false positives, which actually are negatives, that they are benign, but the model sees them as malignant, of which they are actually benign. Now the next metric we shall be looking at is the ROC curve. So let's import the scikit-learn library right here. We import scikit-learn, and then from scikit-learn metrics we import the ROC curve. Also, to plot the ROC curve, we shall be using the validation set data. So we'll move this batch size to 800, or better still 790, since we have 790 data points in our validation set, such that we just have a batch which contains the whole validation set. So from this we run again. After obtaining these results, we have the validation set right here, which we could call again. Then now let's prepare the validation data such that we could plot the ROC curve. So right here we go to the validation data set, and then in this xval and yval lists we put in the x and the y values. So we run this, and then if you print out yval, for example, you see there's this list made of this tensor right here. Now another way to convert all this into a single tensor is by using TensorFlow stack method. So we'll call on TensorFlow stack method, and this is done at axis 0. Run it again, and there we go. We converted that into a tensor, which is of the shape we take in the first. So that's our no output now, which is of shape 790. We also do the same for the x. So let's take this, and then we repeat for the x. Run. See this output. Let's just print out the shape first. So let's have shape. So there we go. We have this our outputs and then the inputs right here. So that said, we have the y true, that's our y target, and then this is our x values or x val. And a way to obtain the y true just suffice to get this, and then to obtain now the y predicted, we have to pass our model on this. So y predicted equals the model.predict of this, since this is our x values. So we'll take that, close the bracket. Now that's okay. So now we have this. Let's print out y true, and then y pred shape, this other one's shape. Run that. We now modify the shape of the y pred so that it matches up with the y true. So there we go. We take all the first axis, and for the last axis we take only the 0th. So here's what we obtain. We are now set to plot our ROC curve. Here we simply use scikit-learn's metrics.ROC curve method, where we pass in the y true, and then we also pass the y pred, so the labels and the predictions. Then from this we'll get the false positive under true positive rates, which now we plot simply. We have false positive rate, true positive rate. We add X level and then the Y level while setting the grid to true. So we could run this, and there we go. This is our ROC plot, which shows on one diagram the different true positive rate and false positive rate pairs our model can have depending on the choice of our threshold. This simply means that if we're building a model in which we have, for example, two delicate scenarios. In the first delicate scenario, we have the patient doesn't have cancer. That is, the patient's cells are benign, but the model predicts that they are malignant cells, hence saying that the patient has cancer. In the second delicate case, the patient actually has the cancer, but the model predicts that the patient doesn't have cancer. We would say that our choice of threshold, that is our choice of whether the fact that a cell is considered to be benign or not, or malignant or not, is based on a threshold value ranging from say 0.1 to 0.9. So, but the most typical threshold we have is 0.5. So what we're saying here is that if we have predicted a value above 0.5 is malignant, below 0.5 is benign. And so since this threshold value we select will modify our position in this ROC plot right here, we have to select it such that it favors our priority. In this case, like generally, we'll prioritize this case where a patient has cancer and the model predicts that the patient doesn't have cancer, because this is very dangerous, as the patient may go back home thinking he or she doesn't have cancer, whereas that patient actually needs to start treatment. So we'll prioritize this over the case where a patient doesn't have, and then we'll say the patient has cancer. So that said, we would want the true positive rate to be as high as possible, mindless of the false positive rate, although we could pick out a certain limit above which we don't want to cross. So if we are trying to focus more on this vertical side, or on having our true positive rate to be as high as possible, such that our model does better in saying that a patient has cancer, then we'll fall on a point like this. So let's pick out this point, for example, and at this point we're practically at almost 1. So this means that our model perfectly, or we could say almost perfectly, is able to see that a patient has cancer. But note that as we do this, the false positive rate increases, whereas if we had decided to be at say this point, the false positive rate will be reduced, whereas the true positive rate too will be below 0.8. So since we are decided to work with the true positive rate as high as possible, for a point we could take from this range, from this point to about this, already we had 1, so no needless continuing, because we want also the false positive rate not to be too high. If not, there'll be so many patients thinking they have cancer when they don't actually have cancer. Recall that the false positive means you don't have malignant cells, but the model says you have malignant cells, so it's a false positive in that case. So we'll settle for this point, or say any point. We could take these points from this range to about this range. So we'll settle for, let's say, settle for this point. We settle for this point. Our true positive rate is almost 1, and then we pick our threshold such that we are at this point. And with that, we show that anytime our model makes a prediction, if a patient actually has cancer, then that patient has almost 100% chance of being diagnosed as a cancer patient. Let's look at another example of how this can be applied. Suppose you're working on a Twitter clone. So you have your Twitter clone, and you have been charged to build a model which classifies non-explicit content, let's say non-explicit image content and explicit image content, such that when people are going through your feeds, when they have explicit content, it is initially turned off, and it's only the user who decides to turn it on and view it. Whereas when we have non-explicit content, everyone can see it directly without having to click on an extra button to view its content. So in that case, if we consider this to be negatives, and then we consider this to be positives. So we consider this to be positives. Also note that the notion of positive and negative has nothing to do with the fact that the content is explicit or non-explicit. As we may be tempted to think that since we have explicit content, then it is negative, and since we have non-explicit content, then it is considered positive. So coming back to our problem, we'll see that we would want that anytime we have an explicit content, we'll want to be able to block it so that only users who want to view can view it. So we prefer to have many false positives, that is, have many non-explicit contents which are initially blocked although they are non-explicit. And this is because we prefer to have this almost 100% probability of blocking all explicit content from being viewed directly. We now get to testing. We'll just pick this image from this folder. Then we use TensorFlow's image to array and load image to obtain the image array. We pass this in our model.predict and we get our model's prediction. Note that this image is a benign, so it's a benign cell. So run this. There we go. This is correct. So we could say if the model predict is less than 0.5, our threshold, then we print it's benign. Else we print malignant. So run again. So that's fine. Now let's continue picking out different images. 3, run, see benign, say 5, and that's it. Now we repeat the same for the malignant. Now we've taken this image. See, here is malignant cell. Paste that. Run this. So that's it. Now we could take other images which are malignant. Say 4. Run that. And then this other one. Say 9. Okay. So we've trained our model, validated, and now on testing. Although we're testing on the training set, we've seen already that our model performed quite well on our validation set. And using the ROC curve, we could pick out a threshold which suits our problem best.